Hello there. Today we're looking at ORPO, Monolithic Preference Optimization without Reference Model. This is a paper by researchers of KAIST AI and largely deals with alignment, aligning language models and instruction-tuned models in some way. We'll dive into what that means. Also, I know there's a paper by Meta released today that deals with another preference optimization topic. So while this isn't that, this should be fairly at least related. So what do we mean by alignment? Alignment can have many different meanings, especially nowadays. It can mean basically whatever you want, but usually things go something like this. You have a language model, and that language model is just a next token predictor, right? It just predicts next tokens. But what people want is some sort of assistant model, something that will take an instruction and follow that instruction. And that's what you do usually with in the first instance, with a technique called supervised fine tuning, which essentially means that you do have demonstrated or some sort of labeled data, if you will. So it's supervised learning. While in language model, you really just have text that you scrape from websites. In supervised fine tuning, you will have something like, okay, there's an instruction and then there is an appropriate answer. And then maybe it's multi-turn, so you have the next instruction and you have the appropriate answer. This here, you can either sort of take a proxy for it, like scrape certain Reddit forums or Quora forums or something like this, or you can actually collect it from humans, like OpenAI has done for their initial InstructGPT papers, or we have done for OpenAssistant, or you can generate it synthetically, or there are all kinds of ways to collect that data. But what we always have is we always have some sort of an input X, which would be like the instruction in that case, and then some sort of an output Y. So you do have demonstrated labeled data for that step. However, there is a third step that is sometimes involved here, which is, in the classic sense, that's the kind of RLHF methods. Nowadays, there are many more methods for that. But what you will end up with a supervised fine-tuned model. With a supervised fine-tuned model, you'll end up with, or with supervised fine-tuning, you end up with a model that, so here is my model, there's a box. When I input, so I can input stuff and it will give me some sort of an output. Now, alignment refers to the fact of making these outputs of the models more in line with what we expect, and notably making the undesired output at this stage less likely. So what is going to happen here is that we input a whole bunch of things, maybe even the same things multiple times, and we'll get out a whole bunch of outputs. So so y hat 1, y hat 2, y hat 3, and so on. And maybe now we have some sort of assessing which one is better, which one is worse, or which one is good, which one is bad. So maybe the humans rank them in order of preference, or what usually happens, we train a reward model that does it for us. So the reward model will say, okay, this is like very good, this is good, and this here, that's bad. And the process of alignment refers to the fact that even though we have a model that, is quite good at language, even though we've actually trained it to sort of follow instructions, we can still improve upon that by making outputs, like answers to instructions that we agree with in some way. That doesn't need to be like agreement in an ideological sense, just that we like. And that preference rating, I deliberately don't tie it to anything. Like, you can tie it to quality, you can tie it to ideology, you can tie it to whatever you want, right? Whatever criteria you want, answers that you approve of to go up in likelihood, and answers you disapprove of to go down in likelihood. This is notably different from supervised fine-tuning, which in a supervised way, it goes from an instruction to an answer to an instruction, right? So different kind of data. Here you have input-output pairs, and here you have different outputs, and you want to make some more likely and some less likely. So this, and yeah, so this here sort of is this process largely referred to as alignment, at least in this paper or in the topic we talk about today. What this paper does is it says, look, these steps, they always need this reference model, this supervised fine-tuning reference model. They may even need a reward model in between, or maybe not, but it's always sort of a multi-step process. So you do the supervised fine-tuning, and then you do the alignment procedure, and so on. And they are going to suggest a method that encompasses not just SFT and RLHF, but sort of the whole SFT plus alignment in one procedure, and that is ORPO. I keep forgetting the acronym right here. That is ORPO. And how do they do that? They do that mainly by looking at SFT and analyzing it and coming up with a hypothesis of why isn't supervised fine-tuning, why can't we just tackle the same data, the same data as here? Like let's say we have always pairs of, so we have X and we have YW, they're going to call it, and YL. So we have a prompt, if you will, and then we have winning responses, like responses that are approved of, and then we have losing responses, which are responses that are disapproved of. And the goal would be to make these more likely and these less likely. Why doesn't supervised fine-tuning work for that in some way? They analyze that, and then they come up with a method to integrate that in supervised fine-tuning so that you don't need 2 steps anymore. That's essentially it. And the results here, while not ginormous gains, as far as I can assess them just from the paper right here, I haven't tried the method myself, but just from the paper, the improvements do seem to be consistent and do seem to make a difference, a notable difference. So yeah, it could be an option. And also notably, you don't need this multi-step thing anymore. You don't need in-between models, and therefore you may even save on compute a little bit while getting better. Okay, so what's the... Well, I wouldn't actually have to have drawn any of this, but you essentially see the same thing right here, where on the left-hand side with RLHF and direct preference optimization, you do have this multi-step process, and with ORPO, you do not, because essentially what they do is just they build one loss from the 2 steps. So they build a joint loss, and then they optimize that loss in one go. So the loss is going to be, maybe that's actually worth it to actually just jump to the ultimate loss they're going to implement, because I think working backwards from there is a bit easier than working forward. So working backwards, here is the loss they propose. This is a loss that you would do during a step that is equivalent to the supervised fine-tuning step, except that you not only need XY pairs, but you actually need preference data. So winning outputs and losing outputs, because you need to do the alignment. You want to know what should you align towards and what should you align away from. What they're going to end up doing is they're going to take the regular supervised fine-tuning loss. We're going to look at that in just a second. And they're going to mix it with this OR loss. OR stands for odds ratio. And there's going to be a hyperparameter trading the 2 off. So the SFT loss is largely going to be responsible for actually creating an instruction following model, right? Not just, remember, this step starts with a plain language model. So you want to make it instruction following and the OR loss is going to make it such that the instruction following happens in a way that you approve of and doesn't happen in a way you disapprove of. And as I said, the data here is going to be some sort of a distribution of prompts, winning responses and losing responses given some method of collecting these, be that humans or synthetic or proxy or heuristic or something like this. So the loss of supervised fine-tuning, maybe that's good looking at that. The loss of supervised fine-tuning is a log likelihood loss. Essentially, what you want to do is you want to input your prompt and you want to have an output that you want to make likely, right? You essentially say, okay, given this prompt, I want this answer to turn out. And what the internally in language models you're going to do is you're obviously going to predict token by token. That's why this gets split up over all the tokens. For each token, you predict it from the prompt and from the last tokens, and you're going to make the log likelihood of this token given this input right here as high as possible. What does that mean in practice? In practice, that means you have your that's your x, then you have that's your y so far, right? And now you need to produce this token right here. So what you're going to do is you're going to take this right here and shove it through a neural network. This is typically going to be some sort of a autoregressive causal attention transformer, but it doesn't need to be. But I guess nowadays that's quite a safe bet to say. So you're going to shove this through some sort of model, and out comes a distribution. Right? Out come these logits, and these logits you would normalize, and then you will find that you will get some sort of distribution. Okay, so I'm gonna make these slightly bigger here so I don't need to draw as many. So you'll get some sort of distribution over your vocabulary, right? Maybe this is cat, this is dog, this is house, this is, and so on. Okay. So each token that could be produced is assigned a probability, if you will, and you're going to select according to this distribution right here. There's going to be a temperature parameter and whatnot. What this log likelihood loss does is it essentially says there's going to be the correct token, correct according to the training data, which is maybe going to be dog right here. I want to make this one higher and everything else lower, right? Every single other token goes lower. So dog goes higher, every other token goes lower. With this loss, can you imagine why models don't automatically get aligned if you just do this? This you can obviously only do on the winning pairs, right? But you might think, well, if I train on the winning pairs, the models should learn that. Why don't they become aligned? Why don't they automatically make the losing ones, which are different from the winning ones, lower at the same time? And here you can see, because it actually makes everything less likely. And since our vocabulary sizes are 32,000 tokens by now or something like this, it means there's going to be one token that's correct, right? And there's going to be one other token. Let's say the YL and the YW actually start with the same few tokens, but then they're different, right? You say, okay, how are you doing? And the one you want to align with is, I am doing just fine. And the one you don't want to align with is, I am terrible today, right? Because you want to train some sort of a friendly, ever-friendly chatbot. You're going to start with I am, and then there's going to be one correct token, and there's going to be one token you surely don't want, right? But this loss essentially does not differentiate the one you surely don't want from all the others that are also just wrong. given if you just look at the winning answer. And they hypothesize, or they propose, that due to this, and they're not the first ones to recognize this flaw in log likelihood loss, but they say, okay, because of this, essentially alignment doesn't happen automatically. Actually, what is probably happening during this procedure is most of these other tokens, the fact that they get pushed down, most of the effect of that is just that the model is going to learn sort of grammar. Now, grammar in itself, it should already know from language modeling, but it's just going to learn kind of the structure and grammar of the type of outputs that you want. Meaning, I give you an instruction and you give me some sort of an answer, some sort of a fulfillment of that instruction. And that will have very often, like, you narrow down the scope of language considerably once you do that. And all of this training right here, what it's largely going to do is just going to make the language model into a general instruction following model, which means the end effect of this is, even though the losing answer is obviously also among all the ones that get pushed down, in end effect, because the losing answer is probably more similar to the winning answer than random output, right? Like all of these others are essentially random output. Because they're more similar, in fact, supervised fine-tuning will also increase the likelihood of the things you don't want to align with. And that is one of the experiments right here. So you can see that log probabilities for chosen and rejected responses during fine-tuning on an RLHF dataset. Despite only chosen responses being used for supervision, rejected responses show a comparable likelihood of generation. So you can see that even the rejected responses, they increase in likelihood, and they do not lag far behind the chosen responses right here. So this failure of supervised fine-tuning to distinguish between pushing up the correct one and pushing down all the others, distinguishing this pushing down all the others from specifically pushing down the one that you don't want to align with, that piece, they say, is missing. So they introduce that piece in form of an auxiliary loss, regularization, not regularization, but just an auxiliary loss that you can add on top of supervised fine-tuning, and you will incorporate that piece of, that desired behavior. Pretty straightforward, but it does mean now you don't need this sequencing of training anymore. The thing they propose here is based on these odds. So the odds of this right here is going to be the likelihood of, so the odds of y given x is the likelihood of y given x divided by 1 minus the likelihood of y given x. So if y given x is any event, the odds tell you how much more likely is the event to happen than to not happen, right? This here is the event happens, and this here is the event does not happen. So if this is 5, it's 5 times more likely that it happens than it doesn't happen, which is 80-something%, I guess. If the odds were 4, it'd be 80-20, but I chose a poor example. Then from that, they can define the odds ratio. The odds ratio is simply the ratio of the odds between two things. So you need two possible outputs, and given the same, I guess this should really say given x, right? So should probably say that. I mean, you can generalize it. You can say the odds ratio between yw given x and yl given x, but you don't need to if you always consider the same prompt here. So the odds ratio is now a ratio. It essentially says how much larger are the odds for the winning output versus the odds from the losing output. That doesn't go directly into the loss, but we're going to do the following. We're going to take the log of the odds ratio, which comes down to just the subtraction of the log odds of each of them. And we're going to put this through a nonlinearity and again take the logarithm of that. Now, there are a lot of logs involved right here, but essentially, I guess this log transforms stuff into the kind of logit space, and this here, if this is, let's say, a sigmoid, nonlinearity, kind of transforms it back into the probability space because it's now between 0 and 1, right? And then this thing right here would push it back to the logit space. I don't know, that's how I imagine it. But it turns out that if they do that, right? So, and then there's a minus sign. So essentially what they want to do is they just want to make that go up, like this part here go up, and then through the minus sign here, it becomes a loss. So they just want the stuff that you want to align with to be more likely than the stuff you don't want to align with given the same prompt. They do a good investigation. They actually calculate out the gradient of this part of the loss, and that can give you some insight of what actually happens during training, right? Because you train with gradient descent. So what's the gradient of this part of the loss? And then we can, once we see the gradient, we can know, okay, to the thing we've demonstrated down here, how will that change if we add that piece of the loss? So what is going to happen? They say the gradient, and they have a full derivation of this, the gradient consists of two different things. The gradient consists of this delta term and this h term. The delta term is the following fraction. Notice the inverse right here. So this is going to be a 1 over this. There's a 1 plus right here, which means that if this thing here is really small, then the whole thing essentially has no effect. However, it's small if this thing is really big compared to the top thing, right? So then it becomes really small. And that means the odds of the losing side, if the odds of the losing side are really big, then this has no effect. If the odds of the winning side are greater than the odds of the losing side, then this in fact does have an effect. So this thing goes up, this thing becomes big, and then this thing, because of the inverse, becomes small. So the whole term is small when we are already correct, and is bigger when we are not yet aligned. So when we're already aligned, when the winning output is very high, then this goes towards 0, and therefore this multiplication goes towards 0, and the whole term has essentially not really an effect. And that's what we want. If we're already aligned, good. However, if we're not yet aligned, then this will go more towards 1, and therefore, so because this here will be big, and then the whole fraction will be small, and then the inverse of 1 plus 0 is 1, and then the whole thing will go towards 1. So here towards 1, and then this has an effect. So this is something between 0 and 1. Now, if it's 1, what is the term that is introduced? Okay, so you can see here, that's the term that's introduced. And it's one gradient minus another gradient. So this term is largely going to push into the direction of this gradient and push away from the direction of that gradient. And as you can see, it's exactly what we want to do. It's going to push into the direction of the winning answer and away from the direction of the losing answer. Both terms are weighted by their own unlikelihood in a way. So the gradient of the winning answer is scaled by 1 minus the likelihood of the winning answer. So if the winning answer is already quite likely, it's going to push it more into that direction. If the losing answer is already quite likely, it's going to push it away more from that direction. Now, I personally am not super sure if this effect over here makes too much sense. Like, but remember, the fraction of up here only really makes the term active when we're not yet super aligned. So therefore, it could be that both are actually very likely, yet it's just a lot more likely to generate the losing answer. In that case, this would pull hard, but then this would also pull hard. So if the model is just really sure about everything, the gradient is going to be bigger in both directions. If the model is not so sure about something, I would guess then it's not so big. I'm not sure if that makes sense or not, like intuitively, but everything up until here, like I can get on board with everything except the things under the fraction right here. Maybe there's a better way of scaling that, but it is what it is in this method. They also discuss this. So they say in equation 10 implies a weighted contrast, a weighted contrast of the two gradients from the chosen and rejected responses. Like, that's very good. Specifically, 1 minus p in the denominators amplifies the gradients when the corresponding side of the likelihood is low. Really? For the chosen responses, this accelerates the model's adaptation towards the distribution of chosen responses as the likelihood increases. Yes, that I can see. It accelerates the model's adaptation toward the distribution of chosen responses as the likelihood increases. That I can get on board with, but here amplifies the gradients when the corresponding side of the likelihood is low. I think isn't this exactly the other way around? Isn't it? So if the likelihood is low, then this is high. No, wait. If the likelihood is... I'm failing at basic math. If the likelihood is low, okay, then that means this thing here is high, which means it does not accelerate the gradient. If the likelihood is low, the thing under the fraction is high, which means that the whole fraction is low, which means it does not accelerate the gradient. 1 minus p amplifies the gradients when the corresponding side of the likelihood is low. Amplifies the gradient. Maybe I'm super confused, or I read something wrong right here, or the sentence got confused. The second part down here I completely agree with. You make your own conclusions. In terms of the results, they do quite a bit of results here. Quite a bit of investigation into different aspects of this, including also some auxiliary experiments on diversity of outputs and things like this. And you can see from the results that they, as I said, sometimes it's not a giant improvement, but it does seem to be a consistent, good improvement, largely across the board, I think. And you can also see that it does pretty well in comparison to models that are larger than itself. So this is a fine-tune or a ORPO alignment of a Mistral 7B model, and you can see that it does compare well or favorably, or at least on par, on the same level as things such as Llama 2, that is 10 times larger. All right, I want to leave it at that. This, I think, concludes the overview right here. They do go into other things. This I found interesting, where they compare it to the probability ratio. You can ask it, why do you go through all of this trouble with the odds and then the odds ratio and so on? Couldn't you just make this a loss term? Like, couldn't you just maximize the probability of the winning stuff, minimize the probability of the losing stuff? If you take the log of this, right? If you take the log of this, you can see that directly becomes the log of PW, let's call it, minus the log of PL. So intuitively, one would have said, well, this is already the SFT loss. Can we just sort of subtract, like just subtract the opposite or do the opposite for the losing output? And it works in like sort of the directional sense, but they also show that for the same pairs of likelihoods, the odds ratio is a much more balanced and flat, if you will, distribution of values, rather than these probability ratios. They tend to get extremely spiky. So as soon as one probability is a bit lower than the other, it's already like quite out of whack. Am I doing this correctly? Oh no, sorry, the other way around. It's just numerically not advantageous to do the probability ratio, but it's, I think, the other way around than I just said. The odds ratio is quite nicely distributed, meaning that for a given difference in likelihoods, you do have a wider range of values to consider, to input, and so on. And if you deal with probability ratios, then you stuck with a narrower range of values that the ratio can take. You can see right here the distribution being super peaky. I guess this is a lesson in how you can frame things, because before I was just saying, okay, how advantageous it is to not have too many values, and I was like, this is so bad because a little change will make a big change in the ratio. But now that I know that they like the different thing, I will say, oh, it's really good that it has a big range in ratio. In any case, I do believe them when they say numerically the odds ratio here is preferable. And they also show that during training, when they train with that additional loss, in general, you can see during training this quantity in itself go up, and then nicely, so remember the graph from before where the rejected responses were like this. Now nicely the rejected responses actually do get rejected. Obviously the big question is, what's the trade-off? Like, how much of what do we lose by adding this loss? There's always a trade-off. The trade-off here might be that the instruction following capabilities in itself might not be as pronounced in these models as they would be if we were to just train with that loss. However, the numbers on the different benchmarks do look okay, in my opinion, and therefore at least you can say, well, maybe to humans that doesn't really matter that much. All right, good. That was it from me. Thank you very much for listening, looking. Please stay hydrated and have a wonderful rest of the week. Bye-bye.